us take some more questions from the chapter Conduction. This will be the second video on Conduction, and we'll solve questions with somewhat a higher difficulty level. Okay, so the first question is from Fourier's law. The question is a plain wall of thickness 250 mm. So this is L. Okay, let me just reduce the size of yeah. So this is L, 250 mm. So I have told you earlier that I like to work in SI units, and so should you, because it actually decreases the probability of committing an error. So L is equal to 0.25 meter and has temperature 1400 degrees Celsius and 100 degrees Celsius on either side. Okay, so this is plain wall. Here the temperature is 1400 degrees Celsius and here the temperature is 100 degrees Celsius. The thermal conductivity of wall is okay. Now the thermal conductivity of wall varies with the temperature. It is not constant. Okay, and it is in watt per meter Kelvin. Okay, calculate the rate of heat transfer through wall. Add in bracket. You have to find it in watt per meter square. That means you have to find heat flux. Okay. So now the thermal conductivity of the wall is varying with temperature. So what do we know? Basic. We just apply the basic Fourier's law, that is Q is equal to minus Ka dt by dx. Okay, this is what I know. Now we have to find this in watt per meter square. So take this A below Q. Okay, so this will be Q by A, that is Q double dash, which is heat flux, minus K dt by dx. Okay, now K is actually varying. The K of this wall is varying with the temperature, so you know that you will have to integrate to get the answer. Okay, so put this K here. This will be 0.81 1 plus 0. This is 0.007 T dt by dx. Okay, the thickness of this wall is 0.25 meters. Okay, and here is Q double dash, which you have to find. Okay, so when you open it, Q double dash is equal to, this will be 0.81 plus this will be 5.67 into 10 to the power minus 3. 5.67 into 10 raised to the power minus 3, again with the dt by dx. Okay, so let's move on to the next page. Yeah. So I'm taking that dx here. So Q double dash dx is equal to, this was what? This was 0.81 plus it was 5.67 into 10 raised to the power minus 3. It is yes, 5.67 into 10 to the power minus 3. Okay, with a negative sign. This is with a negative sign. So this is dt. Okay. Now what are the limits that we can put? Okay, so we can put the limits of length as this is 0 and this is 0.25 meter. Okay, so the limits of x are clear, and the temperature here will be 1400 degrees Celsius, but in this equation K is watt per meter Kelvin. So take care that you have to put the limits of temperature in Kelvin. Okay, this was an important point. So this will be 1400 plus 273, that is 1673 Kelvin, and here it was 100 degrees Celsius, so it will be 373 Kelvin. Heat flows from high temperature to low temperature. Okay, so these will be the limits, 0 to 0.25, and here the limits will be this is 1673 to 373. Okay, adjust the negative sign, interchange the limits, and solve this. So you'll be getting this q double dash 0.25 is equal to, directly interchanging the limits, and it will be 0.81 t plus 5.67 into 10 raised to power minus 3 t square by 2. Limits will be 1673 and the lower limit will be 373. Okay. So solve it. You will get q double dash as, the answer will be 34374.132 watt per meter square. And do check that in which units you have to fill the answer. So here you have to fill the answer in watt per meter square. So this is your answer. Okay. Now there is a short way also in by how you can do this question. There's a short trick also. What you do is that in this equation where t term is given, you put t average. You put t average, but that will be Kelvin only. Okay. So t average will be 1673 plus 373 by 2. Okay. So when you put t average here, what you'll get? You will get k average. Okay. Now directly put the value in Fourier's law and you will get the answer. This is the short trick of this question. So I have explained this conventional method first to give you an insight of the concept, and I have also told you the short trick. Okay. Let's move on to the next question, which is again from Fourier's law. This is a good question. So the question is, a 60-watt lamp buried in soil. The thermal conductivity is 0.83 watt per meter Kelvin at 0 degree Celsius is switched on. So the initial temperature was 0 degree Celsius. Okay. The soil temperature 0.3 meters away from the lamp at steady state is. Okay. So suppose this is the lamp, and when I switch it on, can I say that it will transfer the heat in the radial direction, in all the radial direction? So can I say that it will be, this area will be spherical? It will be conducting heat in the soil in this spherical area. Okay, this was the concept. So earlier the lamp was at 0 degree Celsius, and we will be assuming that the soil surrounding the lamp was also at 0 degree Celsius. Okay, if we can safely assume the soil temperature 0.3 meters away from the lamp at steady state. Okay, so this R is equal to 0.3 meter, where you have to find the soil temperature. Again, apply the basics of the Fourier's law, that is Q is equals to minus Ka dt by dr. Okay, so here A will be 4 pi r square, surface area of sphere. Okay, so it will be 4 pi r square. Okay, and now you have to decide the limits. So take this dr here. Okay, so q dr minus k 4 pi r square dt. Okay, take this r here, so this will be q dr by r square is equal to minus k 4 pi dt. Okay, this k into 4 pi is we solve it, it will be the value will be equal to, this will be 10.43. So this is equal to 10.43 because k is given to you. K is 0.83 and Q is also given to you. What is Q? Q is 60 watt. This will be the total heat that the lamp will be radiating in the spherical area around it. Okay. So this is also given 60. Now you have to decide the limits. Now at R is equal to 0.3, I have to find the temperature. So the upper limits are decided, that R 0.3, okay, and dt will be t. Do we have space? No, I don't have space. So let me drop this. I'll write it very clearly. Now I have some space. So at R is equal to 0.3 meter, I have to find the temperature. Let it be T, okay. But at R is equal to 0, do you know the temperature? No, you do not know the temperature. But here is the trick. At R is equal to infinity. Infinity means that is a very large distance from the center of the lamp, okay, where its heat cannot reach. Okay. So if R is equal to infinity, can I say that temperature here will be 0 degrees Celsius only? That is 273 Kelvin. Because the heat of the lamp will not be able to reach at a very larger distance, which we take it as infinity. Okay. So this was an important point here. Okay. So now we have the limits. Now we have the equation. Solve it, and you will directly get T is equal to, you'll get it in Kelvin, which will be 292.175 Kelvin. 175 Kelvin. And I've told you a lot many times, before filling the answer, check in which units you have to put the answer. So that will be in degrees Celsius. So that is 19.175. 19.175 degrees Celsius. 19.175. This was actually a nice question, because first of all you would be you would be feeling difficulty in writing the area. You will have to understand that the heat will be conducted radially in the form of spherical, in the form of spherical area, sphere area. Okay. And the next part was taking the limits, because at R is equal to 0 you do not know the temperature, but at a very far away distance from the lamp the temperature is still 0 degrees Celsius. So you can directly use that limit. It was a nice question. Next question is, a spherical thin-walled metallic container from resistance circuit diagram. So a spherical thin-walled metallic container is used to store liquid nitrogen at 75 Kelvin. Okay. The container has a diameter of 0.5 meter. The container has a diameter. Okay. Diameter is given, not the radius. So diameter is 0.5 meters. And is covered with an evacuated reflective insulation. Let's draw a rough schematic diagram. This is the container. Here it is liquid nitrogen, which is at 75 Kelvin. This is 75 Kelvin. And its diameter is 0.5 meter. That implies its radius is 0.25 meter. Okay. And it is covered with an evacuated reflective insulation composed of silica powder. Okay. So there is an insulation whose thermal conductivity is given, that is K is equal to 0.017 watt per meter Kelvin. Okay. Thermal conductivity is given. The insulation is 25 mm thick. Okay. So here it is in meters, diameter is in meters. The thickness given is in mm, converted in meters only. Okay. So this is 0.025 meter. Okay. This is the thickness. Okay. So if I write this R1 is equal to 0.25 meter, this R1. Okay. This is R1. So this R2, along with the thickness of the insulation, R2 will be 0.25 275 meters. Okay, and it is a spherical shell, and its outer surface is exposed to ambient air at 30 degrees Celsius. So T infinity is 30 degrees Celsius. Okay, that is 303 Kelvin. Because here the temperature is given in Kelvin, so change this also in Kelvin. So where we were, yeah, 30 degrees Celsius. The heat transfer coefficient on the outside is 20 watt per meter square Kelvin. That is 20 watt per meter square Kelvin. This is also given. The latent heat of vaporization, of nitrogen is 2.05 into 10 to the power 5 joule per kg, and its density is 800 kilogram per meter. Okay. So what you've been asked that the rate of liquid boil off per day is in kilogram per day. Okay, per day, kilogram per day. So the rate of liquid boil off per day. So first of all, let's analyze why the liquid will boil off. Because here the temperature is 30 degrees Celsius and here the temperature is 75 Kelvin. I mean, here the temperature is 303 Kelvin and here the temperature of liquid nitrogen is 75 Kelvin. So heat will go inside this spherical shell from the atmosphere to this liquid nitrogen. So that is why this liquid will boil off due to this heat transfer. Okay. So can I just draw the circuit diagram, resistance circuit diagram. So first of all, we'll be having the convective resistance. Okay. And after that, I will be having the conductive resistance of sphere. Okay. This temperature is T infinity, which is 303 Kelvin, and let this temperature be T1. Let this be T1, which is 75 Kelvin. Okay. Now there's nothing left in this question. I'll write here only. R conduction resistance, conductive resistance of sphere is equal to, you know the formula, that is R2 minus R1 upon 4 pi K R1 R2. Okay, you know R2, yes. You know R1, yes. 4 pi, you know K. Do you know K? Yes, you know K. This K will be of this insulation, which is 0.017 watt per meter Kelvin. Okay, you know K, R1 and R2. So that implies you know conductive resistance. Okay, let's move on to convective resistance. This is equal to 1 by HA. You know this. Do you know H? That is heat transfer coefficient on the outside. Yes, it is 20 watt per meter square Kelvin. And what will be the area? The area will be 4 pi R2 square, because this is the radius. R2 is the radius which is actually in contact with the ambient temperature. Okay, so this will be 4 pi R2 square. Okay, now you know R convection, conduction, T1, T infinity. What you can find? You can actually find the heat transfer rate occurring. Okay, so this will be Q is equal to delta T upon total resistance offered in the path of heat transfer. So this is delta T is 303 minus 75, and this will be R2 minus R1 upon 4 pi K R2 R1 plus 1 by H. Okay. So I'm directly writing the answer. This will be, and you solve it, you put the values, the answer will be 13.353. What will be the units? It will be watt. And what is watt equal to? Joule per second. So that means 13.353 heat is going into that spherical shell per second. Okay, but here you have to find the answer in day. So can I find the heat transfer rate occurring in a day? Yes. Multiply this with 13. 13.353, multiply it with 24 hours into 36. Okay, you will get heat transfer rate in a day. Okay, heat going into that spherical shell in a day. Okay, so this is Q day. This is equal to the value is equal to, let me see the value. This is, I guess, 11.56. Yeah, 11.536 into 10 raised to the power 5 joule per day. So you actually get the heat going into that spherical shell per day. Now it's a game of unit because this is latent heat of vaporization of nitrogen is 2.05 into 10 to the power 5 joule per kg, and you have Q day in joule per day. So Q days in joule per day divided by latent heat HFG, which is in joule per kg. So what you will get, this joule and joule will get cancelled out, and you will get this is liquid boil off. Liquid boil off. Let me rub it. Let me rub this part. So what I have written here. Okay. So I found out Q day. Now I want to find out the rate of liquid boil off per day, kilogram per day. So rate of liquid boil off as m dot kilogram per day will just be equal to the rate going into that spherical shell in a day divided by its latent heat of vaporization. Okay. This is 11.536 into 10 to the power 5. This is in joule per day. Divided by HFG, which is 2.05 into 10 to the power 5. 2.05 into 10 raised to the power 5. This is in joule per kg. Okay. Divided, joule and joule will get cancelled out, and you will get m in kilogram per day, and the value will be equal to 5.63 kilogram. And this was again a nice question. Be careful with the units, they will actually help you a lot. Next question. Okay. The next question is from conduction with heat generation. The average heat produced by oranges ripening is estimated to be 300 watt per meter square. Be careful with the units. This is 300 watt per meter square. Okay. Taking that implies it is Q by A. This is Q by A that you have been given. Taking the average size of an orange to be 8 centimeter, that is its diameter is given as 0.08 meter, and assuming it to be a sphere with the thermal conductivity 0.15 watt per meter Kelvin, the temperature difference in magnitude between the center and the surface of the oranges. Okay, so there is a short trick. I mean, there is a direct formula which you can learn for solving these type of questions, but I will actually derive that formula so you get a better understanding of the concept. Okay, so where that formula actually came from, so you should know this also, and you should know the formula also. So let us start. This is governing heat conduction equation of sphere. Okay, this is by the use of governing heat conduction equation of sphere, which you know is 1 by r square del by del r square del t by del r plus q dot g by k is equal to 1 by alpha delta del t by, this is temperature, this is time. Okay, this is heat generation per unit volume. Be careful, this is in watt per meter cube. Okay. But here Q is given in watt per meter square. So we cannot directly put this value here. Okay. And this is radius, this T stands for temperature. This is the governing heat conduction equation of a sphere. So this is a case of steady state. This becomes 0. Okay. And the equation reduces to 1 by r square del by del r square del t by del r plus q dot g by k is equal to 0. Okay. So take this qg by k here on the right hand side. So this becomes minus q dot g by k. Okay. Take this r square also here. So I am dropping it. This is r square. Okay. Now integrate it. Okay. So you will get r cube by 3 plus c1. Okay. And here I will remove this because we have integrated it. Okay. Now take this r square and divide it on right hand side. So you will get, okay, let me write this now. This will be del t by del r, okay, is equal to minus q dot g r, okay, this is divided by r square, so r by 3k plus c1 by r square plus c1 by r square. Okay, this is del t by del r. Okay. Let's integrate it further to get an equation in temperature. Okay, so this will be t, and this was r by 3k. Okay, r by 3k, so it will be r square by 6k. So q dot g r square by 6k plus this was c1 by r square, so it will be integration of this will be r square minus c1 by r. Okay. So this will be minus c1 by r plus c2. So now we have two constants. Okay, and we have to apply boundary conditions to find those constants. So this is a orange, spherical orange. Okay, and the heat is generated in it from within the center. Okay, so where the temperature is maximum, dt by dr is 0. Okay, this temperature gradient will be 0. Okay, so put this here. If this is 0, r is 0, this is 0, c1 has to be 0. Okay, so c1 is 0. And now what we can do, we can put another equation. The diameter is what? Diameter is 0.08 meter. So radius of the sphere will be 0.04. So can I say at radius 0.04 meter, let the temperature be Ts, that is surface temperature. Okay, put this boundary condition here. C1 is 0 now. So Ts is equals to Q dot G R square. R square is, let it be capital R. So capital R square by 6k plus C2. Okay, so this becomes the second equation. Okay. Now there is one more boundary condition that we can put. We can again put the boundary equation, this boundary equation, that at r is equal to 0, t at center is equal to tc. Okay, so we have actually applied three boundary conditions. One was this, that at center the heat is generated from within the center, so temperature at the center will be maximum. Okay, and that implies the temperature gradient there will be 0. So here, from here we are getting C1 is equal to 0. Then we move on to this boundary condition that at the radius 0.04, the surface radius, the temperature is Ts. So I'll be getting, I actually got this equation. Okay. Then the third boundary condition is that at center, that is R is equal to 0, let the temperature be Tc. Okay. Put this boundary condition again here, you will get Tc is equal to C. So this constant C2 is actually equal to center temperature. Put this condition here, what you will be getting? You will be getting Ts is equal to Q dot G R square by 6K plus Tc. Okay, there is one mistake. This is minus sign. This is minus sign. So when I have changed the page, I didn't take the minus sign. Okay, yeah, this is minus sign. Okay, minus sign. So this is the equation. See the question. What we were finding? We were finding the temperature difference between the center and the surface is. So you directly get this result. Rearrange this equation. You will get Tc minus Ts is equal to Q dot G R square by 6K. Learn this result. Tc minus Ts is equal to Q dot G R square by 6K. And this is what we have to find in this question. Now let's put the values. Do we know Q dot G? Yes, indirectly we do know Q dot G. Okay, because here Q by A is 300 watt per meter square. Okay, so if I multiply this with area, I will get total Q, that is total heat generated. So this is 300 into area of sphere is 4 pi r square. Okay, I know the value of radius, so I will get Q total. Okay, I will get Q total. Okay, now if I divide it with the volume of the sphere, I will get Q dot G, that is in watt per meter cube. Okay. So Q dot G will be equal to 300 into 4 pi r square by 4 by 3 pi r cube. This will be the value of Q dot G, watt per meter cube. Okay. So Q dot G here will be in watt per meter cube. You know the value. R you know, K you know, you will directly get the answer. Okay. So this question was basically done to actually show you from where you get this type of these type of formula. Okay. If you don't want to remember the formula, it will be a bit lengthy. But if you will remember the formula, you can directly put the values and get the answer. But do not forget the basic. Okay, because it's not sure that the IITs will always, ask you to find the temperature difference between the center and the surface. They can ask you to find the temperature between center and at a radius of 0 point something, some value of radius. Okay, so you can still apply that equation in this case also, but my point is, if you remember the basics, it will be better. It will be easy if you by chance forget the formula. So this is how you derive this formula. So its answer will be, I will tell you the answer. Its answer will be 40 degrees Celsius. 40 degrees Celsius. Okay. So you have to find the temperature difference is 40 degrees Celsius. Okay. Next question. It's again a conduction with heat generation question, and the question is a 2 kilowatt resistance heater wire with thermal conductivity, which is 20 watt per meter degree Celsius. Diameter of D is equal to 4 mm, that is 0.004 meter, and a length of 0.9 meter is used to boil water. Now this is wire, that is cylinder. Okay. What will be the temperature at the center of the wire in Kelvin, taking the outer surface temperature of wire as 110 degrees Celsius? Same question based on the previous question, but in this case it is cylinder, not sphere. So the governing equation in this case will be of cylinder, which is 1 by r del by del r del t by del r plus q dot g by k is equal to 1 by alpha. Alpha is thermal diffusivity, lt by del small t. Okay, it's a case of steady state. This will become 0. Q dot g is again in watt per meter cube. Okay, total heat is now given, that is 2 kilowatt, that is 2000 watt. Divide it by volume, you will be getting q dot g. Okay, so this will be 2000 divided by the, what is the volume of cylinder? This is pi by 4 d square l. D you know, L you know, you will get q dot g. Okay, so no problem. R is radius, this is temperature. Okay, again apply the same boundary conditions, you will get the same result. Try it yourself. You will get the, you will not get the same result. You will get the result in the same way. Okay, apply those boundary conditions. The result, final result will be Tc minus Ts will be equal to q dot g. This will be r square by 4k. Here it will be 4k, not 6. Okay. So put the values. R is what? Taking the outer surface temperature. So you have to put the outer radius here. Okay. Outer radius is 0.002 meter. Okay. Q dot g you can find it from here, and K is 20 watt per meter degree Celsius. So the answer will be, you try it yourself, because you can proceed it in the same way. The answer will be, this will be 118 degrees Celsius, which will be 391.8. So this will be the answer, 391.8. Let's move on to the next question. This is two 5 mm thick epoxy boards. Two 5 mm thick epoxy boards. Thermal conductivity is given. Consist of 1 mm thick copper plate. Okay. Let's draw a schematic diagram. This is epoxy. This is epoxy. This is copper plate. This is Cu plate. Okay. This is epoxy. This is epoxy. Thermal conductivity is given 386. Just writing the numerical value. 386 watt per meter degree Celsius, and the thermal conductivity of epoxies is K is equal to 0.26 watt per meter degree Celsius. Okay, the thermal contact conductance on both sides of the copper plate is estimated to be 6000 watt per meter square degree Celsius. Okay. So in the previous questions, what we were doing, we were actually ignoring the contact resistance. But in this question, it is clearly given that the contact conductance on both sides of the copper plate is estimated to be 6000 watt per meter square degree Celsius. So conductance is inverse of resistance. Okay. And see the units. The units are of heat transfer coefficient. Okay. So let's see further what we can do. First of all, we'll read the question. What will be the error involved in the total thermal resistance of the plate when the thermal contact conductances are ignored? Okay. So the first case will be when you will be finding the total resistance including the thermal contact conductance, and the second case will be when you will be ignoring that. Okay. You just have to find the error. So let us draw the resistance circuit diagram with including the thermal contact resistance. This is epoxy. The conductive resistance offered by epoxy. Okay. E. Then there will be thermal contact resistance RC. Then there will be conductive resistance offered by copper RCU. Okay, this is RE. Then again there will be this thermal contact resistance. Okay, this is conductive resistance by epoxy, conductive resistance by copper, contact resistance, and conductive resistance by epoxy again. This is RC and this is R. Okay, let this be case 1. Second case will be, you will be ignoring these contact resistances. So this will be resistance by epoxy, by copper plate, and then again by epoxy. Okay, these are the two cases. First case, second case. Let us now find the thermal conductive resistance of epoxy, copper plate, and this thermal contact resistance. So RE will be L by Ka. Okay, what will be A? There's nothing given about the area, so you can take it as 1 meter square, or you will get to know that if you take it as A only, it will get cancelled out. Why? Because in the end we have to find the percentage. Okay, the percentage. So that means it will be divided by some value which will again contain this term A. So you take it as 1 meter square or you take it as A, it will get cancelled also. Let's take it as 1 meter square. We'll simplify our calculation. This is L by K. L, thickness of epoxy board is 5 mm, that is 0.005 meter, and the plate is, copper plate is 0.001 meter. This is again 0.005 meter epoxy. So this is 0.005 upon K. K of epoxy board is 0.26. Okay, and let's move on to this copper plate. This will be again L by K. So this will be 0.001 by K is 386. Okay, this epoxy again, this will be 0.005 and on 0.26. Contact resistance will be inverse of conductive resistance. So this will be RC is equal to 1 by A. Okay. This A is 1 meter square and this K has actually the units of heat transfer coefficient. So this is RC is equal to 1 by 6,000. And this RC will also be equal to 1 by 6,000. Now you add all these and get the total resistance for the first case. Okay, this will be I should write this will be 0.03. So R total in the first case will be 0.03880 degrees Celsius per watt. We'll be getting this also in degrees Celsius per watt. So this is for the first case. I have to find the error. Okay, I have to find the error if the thermal conductances are ignored. So can I say that R total 1 minus R total 2 by total resistance in case 1 into 100 is my answer directly. Error percentage. Okay, the difference of the resistances in two cases upon the initial case into 100 is my answer. So when I subtract this, you will only be getting twice of contact resistance because other terms will get cancelled out. So this is 2 RC upon R total in the first case, that is 0.3880 into 100. RC is the value of RC, that is contact resistance, will be 0.0000167 degrees Celsius per watt. This you know, so this is 0.03. solve it, the percentage error will be very less, that is 0.88%. And this is why in some cases we ignore the thermal contact resistance. This is the reason. Okay. So this is all for this video. We'll solve some more questions from the chapter Conduction in the third video. Okay. Thank you.